Swayam Prabha. Digital India. Educated India.
Okay, good morning. So we were talking about PLA in the last class. So you may recall that PLA means polylactide or polylactic acid. It is produced from corn to sugars, and then the sugar is converted into lactic acid through a fermentation process using a bacteria. After that, this lactic acid is dimerized into lactide. Okay. Now we have two options. We can take lactic acid and directly polymerize it through polycondensation process, or you take the lactide, which is a cyclic dimer, you open the ring and polymerize it. In the case of polylactic acid derived from lactic acid, you have the issue of formation of water. Okay, presence of water, generation of water during condensation leads to problem with managing water vapor, and also it prohibits the chain growth. That means a long molecular weight PLA cannot be achieved through simple condensation process. But if you look at lactide, that has no such issue. It's a ring opening polymerization, so you can go to very high molecular weight. In both cases, polycondensation as well as in the ring opening polymerization, catalyst and other things are used, okay, which we did not discuss in detail. So what are the challenges in this process? One is lactic acid itself is a chiral molecule, right? It happens to be in D and L type chiral isomers, and we prefer L type, okay, and many times the challenge is to separate these isomers, okay. So you want to predominantly produce 100% L type lactic acid, from there L type lactide, from there L type PLA. That is the ideal scenario. In any of the process I mentioned, from lactic acid to lactide to polymerization, if this stereoisomerization is not followed, then we have a problem of having polymer with a mixed stereoisomers, okay. So that is a key challenge. The other challenge I mentioned was that in the fermentation broth, when you try to get the lactic acid, it is combined with so many other components. So separation of lactic acid from the fermentation broth was the most challenging task. And we also said half of the price in the manufacturing of PLA goes in the separation of lactic acid from the fermentation vessel. Okay, these two things I want to highlight. In this lecture, I want to kind of take it to a more practical scenario that we are going to talk about NatureWorks. It's a company in the US, and they are the pioneers and large producers of PLA. Okay, and I will talk about various product lines they have launched. For that, they have also made resins, and how they describe each resin in terms of physical, mechanical quantities, what kind of equipments are needed, what are the precautions needed, all that has to be mentioned. Okay, so this lecture will be useful if you, let's say you want to make your own pellet, let's say you want to come up with your own resin, how you should present your resin, how you should optimize the property of the resin, we can learn from this lecture. Second is, if you are an end user, you are looking for a PLA based material. It could be film, it could be food container, it could be yarn, it could be 3D printing application. In which case, how do you find your resin? Okay, those are the applications. So now this is what this company claims, NatureWorks, that the raw material is greenhouse gases, that is CO2, okay, and they grow plants from there, and they get dextrose, okay. So they actually do this through corn production, right, and then from dextrose they get lactic acid, from there lactide, and from lactide to polylactic acid or polylactide, and they have a trademark name for the resin called Ingeo. All their products are Ingeo, various codes are given, okay. So this process we have already seen of PLA production. To kind of highlight the important events, so The manufacturing facility of PLA is located at Blair in a state of Nebraska in US, and this plant can actually produce about 150,000 metric tons of Ingeo biopolymers, various grades of Ingeo. And as of now, this nature work is actually combined, jointly owned by two companies. This company Cargill is a agriculture food company in US, big company, and this PTT Global Chemical is a Thailand based company. So they both have co-ownership of this company. So if you look at their research activity and how they became one of the leading producers of PLA, well, in about 1989, Cargill, the company, they were working on a research project. The idea was to use carbohydrates from plants, basically starch and others, as a feedstock, and then how to produce such sustainable plastics. Okay, so as you can see that by 1989, most of you may not have actually born. Even at that time, this thought happened that how to use plant sugars and convert them into a plastic. Okay, and then you can see there's a large gap between 1989 to 2003, and they started this lactic acid manufacturing facility so that they can do a polymerization. And then in 6 years later, in 2009, they also have opened a new application development facility. The application development facility basically tries to optimize the resin parameters, the PLA parameters for an end application, like film rolls, yarns, durable plastics, etc. Okay, and then in 2016, they opened a new fermentation laboratory to develop commercial scale methane to LA fermentation technology. Okay, so now they are, instead of going from CO2, corn, sugar, and then LA, now they are trying to go from methane to LA. So that is something new technology that's happening. So this is their history, right? So now, if you go to their website, in the product line, they show these pictures. Okay, what they say that they have resins that can be used for coating of paper cups. Okay, so many of you might have seen this kind of paper cups in which hot and cold beverages are served. The inner line of this paper would have a plastic coating. Now you will see that usually it is with polyethylene LDPEs, but now we see more and more bio-based coating, and PLA is one such. Okay, so they have resins to coat this paper for this kind of applications. They also have extrusion and thermoforming based applications. We will talk about what are the product lines, and also injection molding, films, yarns, and then 3D printable wires. Okay, so they have resins for all this application. So we'll take one by one in this case. Suppose if you look at the paper coating, the resins for paper coating, they have Ingeo 1102, that is the resin code. Okay, if you want to apply a thin coating of PLA on a paper to make paper cups, you would be looking at this Ingeo 1102 resin. This can be used for extrusion coating on paper as well as paper board, mostly for food contact applications, right? So within this, they have two varieties, 1102A and 1102B. In this 1102A, it has low viscosity and high drawability for improved adhesion, strong heat seal, and lower coat weights. Whereas 1102, it has higher melt strength, toughness for reduced neck-in and greater edge stability in the melt curtain. So when you have this kind of coating for the paper, okay, thickness is very important, finishing is important. If you want to have a very thin coating, you would probably use 1102. Okay, and if you want to have a little thicker coating and higher stability strength, you would use 1102B. Okay, so they have two grades on this. They also say how this has to be processed. Okay, so there's a lot of information about how to handle this resin, what are the properties. For example, they have something called process information for this resin. This 1102, it can be actually processed in a conventional extrusion coating equipment, which could be engineered for LDPE. The existing system would use LDPE as a coating material on paper, as I mentioned before. If you want to use the same extrusion machine, you can do that also, okay, for trial and market development. But you see that in this particular process, you also have to keep this coating little dried, otherwise it will absorb moisture, it will degrade. So you need a new kind of desiccant drying. You also need a little bit of a different screw design and a die design also to minimize this neck-in effect of this polymer. So here is an example. Let's say you have an LDPE and you want to have some 19 micrometer coating, okay, and the density of LDPE is about 0.92. Okay, so that means let's say I have a paper and then I want to coat 19 micrometer LDPE, right? So we can find how much mass is required for coating this. So that mass would be rho times volume. Density is given as 0.92 gram per cc, and volume is nothing but area times the thickness. So let's say area is 1 meter square and thickness is 19 micrometer. So if you do this in terms of so if you do this, you will actually get something like 17.6 grams per meter square of your area. If you take 1 meter square area of your paper, you would use something about 17.6 grams of low density polyethylene. Okay. On the other hand, if you replace this with the PLA, the NGO1002 polymer, you see its density is quite high. Okay. So for the same thickness, the mass you require would be about 23.4. Okay. So that means the amount of polymer that you need to add is actually about 30% more, right? So that's because of the change in the different, that is because of the difference in the density of PLA and LDPE. They also give, suppose if you want to extrude this into a film and then coat it on the paper, they also give all the details of the temperature. The melt temperature should be 230. The feed, there's a hopper in which this pellet is fed. That feed temperature should be, the throat should be 45, feed temperature should be 180. There is a compression section, metering section in the extruder, and those temperature should be maintained. Okay. So if you remember visiting this Ascent material, they are long extruder, and these extruder has a modular sections to be able to change the temperature at different sections. If it's a nylon, you will have a different kind of setting because it is related to the thermal behavior. How do you know this temperature? You have to do DSC, TGA to find what are the melting temperature and what is the viscosity at those temperature, how much shear you want. Based on that, this temperature is the design. So for this particular resin, NGO1002, these are the temperature setting you should have in your extruder. And the process information. So by the way, this picture kind of tells you how this coating happens. So what happens is you have a the green one is the paper, that's a substrate in which you want to coat your polymer. So you see that this paper actually is sent through two rollers. Okay. So you see there's a big roller which is called chill roll, and there is another roller. So it goes in the same direction and the paper gets sucked in. Okay. Now on top of here, you have you will have actually an extruder here. Extruder operating under the temperature that I mentioned in the previous slide. Okay. And the end of this extruder will go through a die, and the die will make a thin film. Okay. So you can construct a die, and through the die the film will come out, and then the film is actually sent through here. This is where when the two rolls actually compress the two substrates and the coating, it gets adhere, and then you draw the film out, and then you would see that bottom is paper, top is your polymer. You can do multiple coating also if you like. Okay. So this is how this extrusion based coating works. Now for this process, the recommendations are the following. This NGO pellet is actually is available in pellet form. it is amorphous at room temperature, but then when you go to about 45, it becomes a little bit sticky. Okay, you can see that all these informations are given to you, so you know what is the temperature to store, what's the temperature to handle. Typically, drying prior to processing is important because there could be some absorption of moisture. Okay, and you cannot send the material as it is, so you may have to do a prior drying process. And also you need to have something called a fume or vent hood over the dye, especially over this place, so that some vapor may actually come out. That has to be handled. Usually if you do LDPE, you don't need all this. You don't need a drying because LDPE doesn't absorb moisture. You don't need a fume hood near the dyeing section because it doesn't give off any vapor. But since this being a biomaterial, it is prone to absorb moisture, it's prone to release some gases when it processes. So, and then sometimes if you see an excessive fuming, it basically means that there is a depolymerization. So PLA gets depolymerized, especially if the temperature goes above 280. So you can see that here we have temperature settings all the way from 230, 45. At the dye temperature is 230. If your heating is not proper, if it's not properly controlled, if the temperature goes above 250, you will see large fumes coming up. That is an indication that PLA gets degraded. Okay, so temperature control is very, very important, and this drying is also very important. Okay, so those are the conditions they have given for the resins for paper coatings. They also give a very detailed recipe about if you have an existing extrusion machine for coating LDPE, and let's say you want to change that machine from LDPE to a PLA, what are the process to follow? Okay, that is also listed out. That means if you ever to make a new resin, alternative resin, PLA like resin, these are the information you should be providing for the user. You should give whether it is operatable in the same kind of an extruder or not, what are the different temperatures in the sections, what are the process conditions, whether we need an additional process like drying and fume hood. Okay, all that information we have to give. So now if you come to this startup and shutdown process, so what you need is that you cannot just use the extruder for LDPE and suddenly switch over. You cannot do that. Okay, so first you have to purge, remove all the previous material, that means LDPE. So here you can see what they do is, let's say at some point of time you have decided to change the line from LDPE to PLA. So usually the coating of LDPE on paper happens with the melt flow index of about 4 to 5. Okay, that means very low viscous, it's easy to coat, it adheres very nicely. So now if you want to replace this with the PLA, don't directly replace with the PLA. First you again do another LDPE which would have much higher viscosity or higher melt flow index. Oh, okay, I think I'm just changing everything. So when the melt flow index is less, it means more viscous, and this is actually less viscous. I think I just changed everything, because melt flow index, what does it mean? It means how much gram of polymer comes through an orifice for an applied weight. If more polymer comes, it means it's less viscous. If less polymer comes out, it means it is more viscous. So when you say melt flow index of 4 to 5, it means it's more viscous material. Okay, whereas the melt flow index from 12 to 16 means it's less viscous compared to this one. Okay, so now the regular coating machine, if that were to be using this 4 to 5 melt flow index, so instead of directly replacing the PLA, what you do is you introduce the less viscous or high melt flow index LDPE coating resins to purge out the more viscous resin at elevated LDPE temperature. Okay, so the regular coating machine is using high viscous LDPE to purge this out. You introduce a low viscous LDPE so that you can actually flush out all the high viscous LDPE. Then stop the extruder and then reduce the temperature to setting for NGO 1002. We know the temperature setting for NGO 1102, and then you cool and then purge briefly with low viscous LDPE again, and then stop pellet flow and continue extruding into waste until screw is empty. Okay, After that, you have to vacuum this hopper system to avoid any trace of LDPE in the hopper, in the feed hopper. After that, you would introduce NGO 1002 biopolymer into the extruder at the same operating condition that you have established in 2. Right, and then once the NGO biopolymer has purged the LDPE, you can optimize the barrel temperature as decided, and then you continue. So you'll have a continuous production of PLA film. At some point of time, you may want to switch from PLA to LDPE again. So in this case, at shutdown, you purge the machine with LDPE resin at the low NGO temperature before resetting the standard LDPE. Right. So a detailed process is given how you should switch from a currently running LDPE based coating to PLA and coming back to LDPE again. Right. Now we go to second kind of resin. This is series 2000 NGO 2003D. I am giving only one example. There are few other resins in this series also. This is a thermoplastic resin and is specially designed for fresh food packaging, food serviceware applications, including dairy containers, that means curd and milk, hinged ware, that means clamshells for sandwich packaging, cold drink cups, juices, and so on. So in this case, conventional extrusion can be used, and the extruded film that you produce from this machine, you can use what is called thermoforming easily. Okay, and they also given what should be the extruder dimension. There are screws available for extruder, which we call this as general purpose screw with no special design, with the length to diameter ratio of 24:1 to 32:1. So you go to market, when you want to describe an extruder, you will say whether you would have special purpose or a general purpose screw. Then you say what is the dimension of the screw. You have to give a aspect ratio, the length to diameter ratio. That's what this is. You also have to give a compression ratio 2.5 to 3:1, and the barrels can be either smooth or rough depending upon what kind of mixing and shear condition you want. So if you want to set up a extrusion machine for processing this NGO kind of polymer, these are the specifications you would be telling your extruder manufacturer. Okay, and this particular resin, you can see density is about 1.24, melt flow index is about 6, melting point temperature is given. It is mostly a transparent film or transparent container, and then you can see that the properties, the tensile strength is about 53 megapascal, yield strength is about 60 megapascal, tensile modulus is about 3.5 gigapascal, elongation at break is about 6, that means it's not too flexible. Okay, LDPE can go up to 900 to 1000%, okay, but this can only go 6 times, 6%, and then there are impact and distortion temperature. So all these mechanical properties, thermal properties are also available to you. The third is to look at resins for injection molding. There are some certain products that you want to do injection molding, okay, like cutleries, cups, plates, and cosmetics, tubes, all kinds of things. For that, you need a 3000 series NGO, and it is designed for specifically injection molding applications. And these resins can be used in the conventional injection molding machinery. Okay, so in this case also you can see this type of resins density is not very different from previous cases. It's always 1.2, 1.3, 1.24 and all that. But if you see melt flow index is quite high. If you want to do injection molding, you want the polymer to flow like a liquid so that you can go and fill all the mold regions. Okay, if you go back here, in the case of extrusion and thermoforming, the melt flow index you need is only 6. Okay, it's going to be very high viscous melt, okay, for this application. But if you do injection molding, it has to really flow like a liquid, simple liquid. Okay, so that's why you can see that a big difference in the melt flow index. So the container will be transparent because it's crystallized and all that. If you look at the yield strength is about 62, but the elongation at breakage is only 3.5%. That means it's going to be quite brittle. For this kind of application like cutlery and cups, you're not expecting a lot of stretching requirement anyway. and flexural modulus, flexural strength is also reported. Okay, so basically you have to see whether the product that you are going to make requires this kind of properties or not. Okay, if it matches, then you can use this resin. That's all we are trying to say. They also have resins for other types like oriented films, cardstocks, and graphic cards. And they can actually make this ingeo films, which could be heat sealed at 80 degrees Celsius all the way up to 150 degrees Celsius, depending upon whether it is a simple film or it is an oriented film. The clear films have excellent optics and shrink machinability as well as excellent twist. And these films can be used for barrier films for oil and grease. So here you can see that this film application, this is not actually injection molding. Okay, so this is for resins for films, and you can see there are a lot of grades for high heat film, general purpose film, and for heat seal layer for film also. Okay, all that is possible. Then there are also resins for biomedical applications like tissues and medical textiles, fibers, non-woven clothes. So here the resins are designed for fiber processes to form mono or multi filaments, as well as spun bound and melt blow down products. And in this case, melting point ranges from 130 to 170, and you can have both amorphous to crystalline grades. So here this list gives you all kinds of this is an emerging application for them. So you can see a lot of innovation, a lot of new kind of designs. Each resin has a particular application. For example, if you take this 6060D, it is the amorphous low melt for staple fiber sheath layer with no special purpose. But if you look at this 6500D, this is a softer feel. It gives a good comfort and it has an improved tensile strength, usually used for tissue, hand tissue and applications, right? So one would look at this list of resins availability and then see whether the application that you have in mind can be met from these kind of resins, right? Okay, so that's all I have. So I think the point is just to summarize. So Nature Works is the biggest producers of PLA. Okay, and they use corn to sugar to lactic acid to lactate to polylactic, and they have about 6 product range resins for 6 different product range. For each product range, there are information about the resins property, mechanical, thermal properties, and then also specification about what are the equipments needed, what are the specifications, temperature ranges, process conditions. Okay, so it's quite useful in that sense that if you want to convert any product into PLA based, you can choose the resins from this list and then go and talk to your extruder and then see whether they can make this extruder for you. Okay, so okay, we'll stop here.